Welcome. The BoreCore archive is a collection of slow, methodical recordings of technical processes and perfectly boring routines designed to help you relax and fall asleep. New procedures are added regularly, so don't forget to like and subscribe. Time to relax, close your eyes, and take it on down to Sleepy Town.
Welcome to a complete operational guide to the daily management, water quality monitoring, feeding, disease prevention, spawning, egg incubation, fry rearing, and stocking operations of a state salmonid fish hatchery, or keeping several million fish alive simultaneously, one water test at a time. You are a fish culturist at a state-operated salmonid hatchery. Your title, fish culturist, is the professional term for the person who raises fish in a controlled aquatic environment for the purpose of supplementing wild populations in streams, rivers, and lakes open to public fishing. Fish culture is the practice. The hatchery is the facility. You are the person who runs it. Your hatchery sits on a cold, spring-fed creek in the mountains of the Pacific Northwest, at an elevation that keeps the water at a consistent temperature year-round. The creek contributes the primary water supply for the facility. The hatchery has been in continuous operation since 1938, which makes it older than most of the trees visible from its grounds, and considerably older than you. It was built by the Civilian Conservation Corps during the Depression as a federal project, and transferred to the State Fish and Wildlife Agency in 1952. The main hatchery building, the raceways, and the spawning building are all original construction, modified and expanded several times over the decades, but recognizably the same facility that crews with horse-drawn equipment built on this creek 87 years ago. The hatchery produces 4 species: rainbow trout, Oncorhynchus micus, brown trout, salmotrutta, coho salmon, Oncorhynchus kissach, and steelhead, which is the anadromous or sea-run form of the rainbow trout, and is technically the same species, but managed as a distinct stock because of its migratory life history. In total, the hatchery releases approximately 4 million fish per year into streams, rivers, and reservoirs throughout the state. 4 million fish over the course of a year, produced from eggs through juvenile stages to release size, is a number that is easy to say and somewhat harder to fully appreciate without standing in the middle of a raceway, holding a feeding paddle, while 40,000 fish break the water's surface simultaneously in a dense, silver-flickering mass. Your permanent staff consists of 4 people. You, a senior fish culturist who has been here for 22 years, a junior fish culturist who has been here for 3, a hatchery maintenance specialist who manages the physical infrastructure of the facility, and an administrative assistant who handles the paperwork, the fish transportation, scheduling, and the interminable reporting requirements of a state agency. During the spawning season, which runs from October through January, depending on species, the agency sends 2 seasonal workers to assist with the spawning operations. During the summer rearing season, a summer intern from the State University Fisheries Program assists with daily operations. The 4 of you and the seasonal assistants are responsible for 4 million fish. Today is a Tuesday in early March. The coho salmon eggs incubating in the hatchery building have been hatching for the past 4 days and are transitioning from the egg stage to the alevin stage, the stage in which the newly hatched fish absorb their attached yolk sacs. The rainbow trout in the outdoor raceways are in active rearing, approximately 6 months from their projected stocking date. The steelhead smolts, which have been rearing since last spring, are approaching smoltification, the physiological transformation that prepares them for migration from freshwater to the ocean. The brown trout are in early fry stage. You have, at this moment, 4 species in 4 life stages simultaneously. This is normal. Let us begin. You arrive at the hatchery at 6:30 in the morning. You arrive at this time every morning, including weekends, because fish do not observe the work week, and the morning mortality check is the most important routine task of the day. A fish that died overnight is a fish that must be found and removed before it can begin to decompose and spread disease to its neighbors. In a raceway containing 40,000 fish, the difference between finding 10 dead fish in the morning and finding 100 dead fish 2 days later is the difference between a minor mortality event and an outbreak of a bacterial infection that can kill thousands of fish before it is controlled. You do not miss the morning check. In 22 years, you have missed it twice, both times due to a medical situation that your junior colleague covered. Both times, there were no unusual mortalities. You note this not with relief, but with the understanding that the streak of unremarkable mornings is maintained by the morning checks themselves. You park, put on your waders, and walk the facility. The hatchery grounds in early morning in March are quiet except for the sound of water moving through the distribution system and the particular sound of a large number of fish in a confined space, which is not a loud sound, but a pervasive one. A continuous soft disruption of the water surface, a collective breathing and moving that is felt as much as heard when you stand at the edge of a well-stocked raceway. You begin at the outdoor raceways, which are the long, rectangular concrete channels that hold the larger juvenile fish. Your hatchery has 12 outdoor raceways, each approximately 100 feet long, 12 feet wide, and 3 feet deep, fed by a constant gravity flow of spring water from the distribution system. Each raceway holds between 30,000 and 60,000 fish, depending on species and size. Governed by the carrying capacity of the water supply at the current flow rate and temperature, the raceways are arranged in 2 parallel rows of 6, and you walk the length of each one, watching the fish behavior and scanning for mortalities. Healthy fish in a raceway exhibit a specific distribution pattern. They orient facing into the current, distributed fairly evenly through the water column, moving with a characteristic regular tailbeat that maintains their position in the current. A fish that is sick or dying deviates from this pattern in recognizable ways. A fish that is swimming near the surface, on its side, or at an unusual angle, is exhibiting a distress behavior associated with swim bladder dysfunction, neurological damage, or terminal disease. A fish that is hanging motionless at the tail end of a raceway, where the current is slowest, may be weak from disease or inadequate feeding. A fish that has settled to the bottom is almost certainly dead or nearly dead. You watch for these deviations as you walk each raceway. In Raceway 3, which holds rainbow trout at approximately 4 inches in length, you observe 3 dead fish near the tail end screen, the mesh barrier that prevents fish from escaping into the drain. You remove them with a long-handled dip net and examine each one. Dead fish are not simply discarded. They are examined for the cause of death, which provides information about the health of the population they came from. You squeeze each fish gently along its body, checking for softness or unusual texture. You examine the gills, which should be bright red in a recently dead fish. You look at the external surface for lesions, hemorrhage, unusual coloration, or eroded fins. The 3 fish from Raceway 3 have pale gills, which indicates they have been dead for some hours. And 2 of the 3 have minor fin erosion at the base of the dorsal fin, which is consistent with a bacterial condition called fin rot, caused by Flavobacterium columnar, a common opportunistic pathogen in hatchery salmonids. Fin rot is not an emergency finding. It is a common condition in hatchery fish maintained at high density, particularly during periods of environmental stress, such as temperature fluctuations or handling. You note the observation: 3 mortalities in Raceway 3, 2 with dorsal fin erosion, consistent with columnaris. You will monitor Raceway 3's mortality rate over the next several days. If the daily mortality count increases significantly above the normal background level, you will treat the population with an appropriate antimicrobial. The normal background mortality rate for a healthy raceway of juvenile rainbow trout at this size is approximately 0.05% per day, meaning roughly 20 fish per day in a raceway of 40,000. 3 fish overnight is well below that threshold. You note it and continue. You complete the mortality check in all 12 outdoor raceways and in the indoor tanks holding the smaller fry and the incubating eggs. Total morning mortalities across the facility: 18 fish. This is a satisfactory number. You bag the mortalities for disposal in the hatchery's composting system, which converts fish waste and mortalities into fertilizer used on the hatchery grounds. you return to the main building to begin the water quality testing. Water quality is the foundation of everything that happens at a fish hatchery. The fish in your care are entirely dependent on the water you provide them. Its temperature, its oxygen content, its chemistry, and its freedom from contaminants. A water quality failure in a fish hatchery is not an abstract concern. It is a concrete emergency with a timeline measured in minutes for some parameters and hours for others, and a consequence that can be the loss of thousands of fish before the situation is corrected. You test the water every morning, every afternoon, and any time a behavioral cue from the fish suggests something may have changed. The primary water source for the hatchery is the spring-fed creek that runs through the property. Spring water has the considerable advantage of temperature stability. The creek at the intake maintains a consistent temperature of approximately 51 to 53 degrees Fahrenheit throughout the year, warming only slightly in late summer and cooling slightly in late winter. This temperature range is ideal for salmonid culture, cold enough to slow pathogen growth and support adequate oxygen solubility, but warm enough to support acceptable growth rates without requiring supplemental heating. The consistency means you can plan your production calendar with confidence that temperature-related growth projections will be accurate. Your primary water quality concern is dissolved oxygen. DO, dissolved oxygen, is the oxygen dissolved in water that fish extract through their gills to support their metabolic processes. Fish require a minimum dissolved oxygen concentration to survive. For salmonids, the minimum is approximately 5 milligrams per liter, and the preferred range for active growth is 7 to 11 milligrams per liter. Below 5 milligrams per liter, fish begin to exhibit stress behaviors, reduce feeding, become susceptible to disease, and below approximately 3 milligrams per liter, begin to die. The oxygen demand of a raceway containing 40,000 fish is substantial, and the incoming water, despite its cold temperature and relatively high initial oxygen saturation, can be significantly depleted by the time it exits the raceway if the fish density is too high or the water flow is insufficient. You test dissolved oxygen with a polarographic dissolved oxygen meter, a portable electronic instrument that you carry during rounds. You insert the probe into the water at the tail end of each raceway, which is the point of lowest oxygen concentration. Because the fish have been extracting oxygen from the water throughout its passage through the raceway, and you record the reading, the tail end oxygen concentration is the critical measurement because it represents the worst case oxygen exposure for the fish nearest the outlet. If the tail end reading is acceptable, the oxygen throughout the raceway is acceptable. Raceway 1, 9.2 milligrams per liter. Raceway 2, 8.8. Raceway 3, 9.1. Raceway 4, which holds the densest population at the moment, a group of 6-inch rainbow trout that were recently consolidated from 2 raceways, 7.4 milligrams per liter. 7.4 is above the stress threshold, but lower than you would like. You check the flow rate to Raceway 4 by timing the filling of a 5-gallon bucket at the raceway's drain. Flow rate is approximately 480 gallons per minute. The design flow for Raceway 4 at this fish density is approximately 500 gallons per minute. The flow is slightly below target, which accounts for the somewhat low dissolved oxygen. You check the supply valve and find it is at 92% open rather than the full open position. You open it fully. Flow increases, and you note that it is now approximately 505 gallons per minute. The dissolved oxygen at the tail end, measured 15 minutes later, has risen to 8.1 milligrams per liter. You note the correction in the daily log. Water temperature is your second critical parameter. You record the temperature at the water supply intake at the head end of a representative raceway and at the tail end of a representative raceway. The temperature difference between head and tail end is typically less than 1 degree Fahrenheit in a well-managed raceway, which indicates adequate water exchange and prevents the accumulation of metabolic heat from the fish population. This morning's temperatures are: intake 52.1 degrees Fahrenheit, raceway head end; 52.3 degrees Fahrenheit, raceway tail end; 52.8 degrees Fahrenheit. The temperature rise through the raceway is 0.7 degrees, which is within the acceptable range. You also test for total ammonia nitrogen, TAN, which is the combination of ammonium ion and unionized ammonia produced by fish as a metabolic waste product. Unionized ammonia, NH3, is the toxic form, and its concentration in the water depends on both the total ammonia concentration and the pH. At the pH of your water, approximately 7.4, approximately 4% of total ammonia is present as unionized ammonia. You test the total ammonia at the raceway tail end using a colorimetric reagent kit that produces a color in proportion to the ammonia concentration. This morning's total ammonia at the tail end of Raceway 4, your most densely loaded raceway, is 0.8 milligrams per liter. At a pH of 7.4, unionized ammonia is approximately 0.03 milligrams per liter. The chronic toxicity threshold for rainbow trout is approximately 0.02 milligrams per liter of unionized ammonia. You are slightly above the chronic threshold in Raceway 4. The density reduction from the recent consolidation has not yet fully normalized the ammonia load. You note this. The flow rate increase should help. You will retest this afternoon. Feeding is the activity that most visitors to a hatchery recognize and most misunderstand. When people imagine feeding fish at a hatchery, They imagine something gentle and pleasant, which it is at the scale of a garden pond, at the scale of a hatchery containing 4 million fish in various stages of development. Feeding is a precisely calculated, physically demanding, carefully timed operation that determines the growth rate, the feed conversion efficiency, the health status, and ultimately the survival and quality of the fish you are producing. The hatchery uses commercially manufactured dry pelleted feed for all fish beyond the first feeding stage. The pellets are formulated specifically for each salmonid species and each life stage with protein content, typically in the range of 42 to 48% from fish meal poultry byproduct and plant protein sources, a fat content of 15 to 22% from fish oil and plant oils, and the balance from carbohydrates, minerals, and vitamins. The pellet size is scaled to the fish size. Newly feeding fry receive crumble, a fine powder-like particle of approximately 0.3 to 0.5 millimeters. And as the fish grow, they are progressively moved to larger pellet sizes, up to 5 or 6 millimeters for the largest pre-release fish. The daily feed ration is calculated as a percentage of the fish population's total body weight, called the feeding rate or the biomass feeding rate. The appropriate feeding rate varies with water temperature because fish are ectothermic, meaning their metabolic rate is driven by environmental temperature, and warmer water means faster metabolism, higher appetite, and a higher appropriate feed ration. At 52 degrees Fahrenheit, the appropriate feeding rate for rainbow trout in active growth is approximately 1.4 to 1.6% of body weight per day. This means that a raceway holding 40,000 fish with an average weight of 40 grams, which is approximately 1.4 ounces, has a total biomass of approximately 1,600 kilograms. And the daily feed ration is approximately 1,600 kilograms times 1.5%, which is 24 kilograms of feed per day for that raceway. You use a feed table, published and periodically updated by the hatchery program's nutritionist, that specifies the daily feeding rate for each species at each temperature and each life stage. The table adjusts for temperature in 2-degree increments and for fish size in weight categories. You look up the appropriate rate each morning after recording the water temperature, and you adjust the feed calculation accordingly. A temperature change of 2 degrees Fahrenheit corresponds to an adjustment of approximately 10 to 15% in the feeding rate. In the spring, as water temperature gradually increases toward the warmer months, you increase feed rations incrementally on a schedule that tracks the temperature trend. In the fall, you reduce them. The fish are not consulted on this schedule, but they respond to it in the manner of animals responding to their environment. They eat what is available at the rate their physiology allows. Feeding method varies by fish size. The smallest fry in the indoor tanks are fed using demand feeders, devices mounted over the tanks that dispense small quantities of feed. Whenever a fish triggers a pendulum mechanism by bumping it with their nose or body, demand feeders provide continuous ad libitum access to feed, which maximizes feed intake and growth rate in small fry that have high metabolic rates and small stomach capacities requiring frequent small meals. The demand feeders are filled every morning and afternoon, and the trigger sensitivity is adjusted weekly as the fish grow and the feed particle size is increased. Larger fish in the outdoor raceways are fed by hand broadcasting, automatic feeders, or a combination. You feed the 4-inch rainbow trout in raceways 1 through 6 by hand, broadcasting the calculated ration in 3 to 4 passes along the length of the raceway using a long-handled broadcast scoop. Broadcasting feed by hand allows you to observe the fish response to each handful. Are they actively rising to the surface to intercept the pellets? Or are some pellets sinking uneaten to the bottom? Active surface feeding indicates hungry fish and appropriate ration. Significant sinking of pellets indicates overfeeding or reduced appetite, which can be an early sign of disease, temperature stress, or spawning readiness in older fish. You watch the surface of the water throughout the feeding pass with the focused attention of someone reading a text in a language they have read for 22 years. But that still occasionally presents new sentences. Raceways 7 through 12, which hold the larger steelhead smolts, are fed by automatic belt feeders mounted on a rail above the raceways. The belt feeders are programmed to dispense feed at a controlled rate over a specified period, typically 2 to 4 hours in the morning and 2 hours in the afternoon, with the total daily ration divided between the 2 feeding periods. The programmed ration is calculated by you each morning based on the feed table and the current water temperature, and adjusted if the fish behavior during hand observation suggests a need for more or less feed. You stand at the raceway for 5 minutes after the automatic feeder starts each morning to verify that the feed rate and fish response are consistent with your expectations before moving on to other tasks. Feed conversion ratio, FCR, is the metric by which feeding efficiency is evaluated. FCR is the weight of feed consumed divided by the weight of fish gain. An FCR of 1.2 means that 1.2 kilograms of feed produced 1 kilogram of fish growth, which is an excellent conversion ratio for salmonids. An FCR above 1.6 indicates inefficiency, usually from overfeeding, underfeeding, disease, or poor feed quality. You calculate the FCR for each raceway group at each monthly weighing and record it in the production database. Historical FCR data allows you to detect declining feed efficiency before it becomes a significant production problem. After feeding the outdoor raceways, you enter the incubation building. The incubation building is a long, low structure with a concrete floor, maintained at a consistent cool temperature by the ground contact, and the cold water flowing through the equipment inside it. The building holds the egg incubation trays and the early fry tanks for all 4 species, representing the most vulnerable and most carefully monitored life stages in the hatchery's production cycle. Salmonid eggs are incubated in stacked tray incubators called Heath stacks, or simply stacks, which are the industry standard for salmonid egg incubation. A Heath stack consists of a vertical series of perforated aluminum or fiberglass trays, each approximately 14 inches by 18 inches, stacked in a frame and supplied with a constant upwelling flow of clean, oxygenated water from below. The eggs rest on the perforated tray surface, and water flows up through the perforations around the eggs, providing oxygen and removing metabolic waste. The stack design allows a large number of eggs to be incubated in a small physical footprint. A standard 6-tray stack holding eggs at the standard density of 2 eggs per square centimeter can hold approximately 8,000 to 10,000 eggs in a footprint of 2 square feet. The coho salmon eggs that have been hatching for the past 4 days occupy 24 stacks in the central section of the incubation building. The eggs were spawned in November, fertilized, water hardened, and placed in the stacks at an initial density of 2 eggs per square centimeter. Over the incubation period, which at your water temperature of 51 to 52 degrees Fahrenheit takes approximately 600 accumulated thermal units to reach the eyed stage, and approximately 1,200 accumulated thermal units to reach hatch. The eggs develop through a well-characterized sequence of stages that you monitor daily. Accumulated thermal units, ATUs, also called temperature units, or TUS, are the product of the water temperature in Celsius and the number of days at that temperature, summed over the incubation period. They provide a species-specific developmental clock that is independent of the actual calendar time and depends only on the thermal history of the eggs. At 52 degrees Fahrenheit, which is approximately 11 degrees Celsius, your coho eggs accumulate 11 TUS per day. The hatch threshold for coho is approximately 450 TUS after fertilization. The current coho eggs were fertilized approximately 45 days ago, giving them approximately 495 accumulated TUS, which explains why they are hatching now. You examine the hatching stacks. The transition from egg to alevin is not instantaneous. Over a period of several days, an increasing proportion of the eggs in each tray hatch as the accumulated thermal unit threshold is reached by individual eggs. You observe the trays. Approximately 70% of the eggs in the upper trays have hatched. the alevins lying among the remaining intact eggs, their yolk sacs large and amber-colored, their eyes visible, but their bodies still translucent. The remaining unhatched eggs are white if they are dead, opaque milky white rather than the clear amber color of the healthy eggs, or they are still clear and viable, recognizable by the visible eye spot in each one. Dead eggs must be removed daily from the incubation stacks because a decomposing egg produces fungal growth, specifically saprolegnia, a water mold that spreads rapidly to adjacent viable eggs. Saprolegnia infection of incubating eggs is one of the most significant causes of egg mortality in hatcheries and requires vigilant dead egg removal and, when necessary, treatment with approved fungicides. You examine each tray carefully for the white, cottony growth characteristic of saprolegnia. This morning, you find a small saprolegnia colony on the surface of one tray in stack 14, associated with a cluster of dead eggs near one corner of the tray. You remove the dead eggs with a fine-tipped tweezers, removing each one carefully to avoid disturbing the living eggs or alevins around them, and treat the affected tray surface with a brief rinse of a dilute iodophore solution, approved for use on incubating salmonid eggs and effective against saprolegnia. You note the finding in the egg incubation log and flag stack 14 for closer monitoring over the next several days. You also check the egg counts in each stack, reading the tray counts from the labels attached during setup and adjusting the record for daily mortalities removed. The total coho egg count at the start of incubation was 182,000 eggs across the 24 stacks. Current mortality log shows 2,040 eggs removed to date, giving a current survival of approximately 98.9%. This is an excellent egg survival rate. The industry standard for acceptable coho egg survival through incubation is 85% or better. You are well above standard. The coho alevins that have been hatching over the past 4 days represent a critical transition point in the production cycle. An alevin is a newly hatched salmonid fish that retains its yolk sac, the nutrient reserve absorbed from the egg during incubation. The yolk sac provides the alevin's entire nutritional requirement for the first several weeks of its post-hatch life, during which the alevin does not feed externally, but instead absorbs the yolk internally. The alevin stage ends when the yolk sac is fully absorbed, at which point the fish becomes a fry and must begin feeding externally, or it will starve within a few days. The transition from alevin to first feeding fry is one of the highest mortality windows in salmonid culture, because fish that do not begin feeding at the appropriate time, when they have enough energy remaining from the yolk to actively pursue food, will rapidly deplete their reserves and die. The timing of first feeding presentation is therefore critical. You want to offer feed to the alevins slightly before the yolk sac is fully absorbed, ensuring that the fish have begun to associate the sight and smell of food with feeding before they are actually nutritionally dependent on it. For coho at your water temperature, the yolk sac is fully absorbed at approximately 800 accumulated thermal units post-hatch, which at 11 thermal units per day is approximately 73 days post-hatch. You typically begin offering feed at around 700 accumulated thermal units, giving a 10-day window for the fish to begin feeding before the yolk is completely gone. You monitor the yolk sac absorption by observing the alevins in the hatching trays under magnification. The yolk sac is visible as an orange-amber protrusion from the ventral surface of the fish. As absorption progresses, the yolk sac diminishes in size over a period of days until it is no longer visible and the fish's body profile becomes uniformly cylindrical. This morning, you examine a sample of alevins from the earliest hatched trays, those that began hatching 4 days ago. The yolk sac on these fish is approximately 40% of its initial size. You are not yet at the point of beginning feed presentation, but you note the progress in the alevin log. In approximately 10 to 12 days, you will begin placing small quantities of crumble feed on the water surface above the trays, initially at a rate barely visible to the eye, and observe whether any fish are beginning to show interest in the food. The first feeding of coho fry is one of the most labor-intensive periods of the production cycle. During the 10 to 20 days surrounding the critical first feeding window, you make multiple feeding observations per day, watching for the characteristic darting behavior of a fry that has successfully ingested a food particle and is responding to the stimulus of external feeding for the first time. You look for fish that are oriented toward the water surface and making upward strikes at floating particles. Once you observe the first feeders, you increase the feed presentation rate incrementally over several days as more fish begin feeding, until the entire population is actively feeding and can be managed on a demand feeder. The period between the first visible feeder and 90% of the population feeding reliably is approximately 7 to 10 days. And during this window, you are in the incubation, building multiple times each day, watching fish eat. The brown trout fry in the indoor rearing tanks have been feeding for 3 weeks and are now at approximately 200 thermal units post-first feeding. A fully established feeding population taking crumble actively at every feeding. You observe the morning feeding of the brown trout. You drop a small pinch of crumble at the water surface and watch the response. The fish swarm to the surface in a dense competing mass, each fish striking at particles, some missing, and turning to attempt a second strike. The water surface broken into a fine chaos of small splashes that subsides as the crumble settles through the water column and the fish follow it down. Active, competitive surface feeding is the behavioral indicator of a healthy, well-nourished fry population. You are satisfied with what you see. The steelhead smolts in raceways 7 through 12 represent the most biologically complex population at the hatchery at this moment, because they are in the process of a physiological transformation that is arguably the most remarkable metamorphosis in a freshwater fish's life history. Smoltification is the suite of physiological, behavioral, and morphological changes that prepare an anadromous salmonid for the transition from fresh water to salt water, a transition that the fish will make when they migrate downstream to the ocean, and that would kill an unsmolted fish within hours of saltwater exposure. A steelhead parr, which is what the fish in your raceways have been for the past 9 months, is physiologically adapted for freshwater. Its kidneys produce large volumes of dilute urine to compensate for the constant osmotic influx of water through its gill membranes, and its gills actively absorb ions from the relatively ion-poor freshwater to maintain the fish's internal salt concentration. A saltwater environment presents the opposite challenge. The fish is now osmotically losing water to the surrounding seawater, and its physiology must switch from absorbing ions at the gill to actively excreting them. A fish that undergoes smoltification is essentially building a completely different osmorgulatory system from scratch, driven by seasonal photoperiod cues and hormonal cascades involving cortisol, thyroid hormone, and growth hormone. The external signs of smoltification that you monitor in your steelhead populations are visible and measurable. The first is silvering. The parr markings, which are the dark vertical bars called parr marks that juvenile salmon and trout have on their flanks, and that serve as camouflage in the dappled light of a stream, fade and are replaced by a uniform silver coloration as guanine crystals are deposited in the skin. A parr that is completing smoltification becomes noticeably more silvery and reflective. The second sign is the characteristic body form change. Smolts become more streamlined, with a more deeply forked tail and a narrower body profile, consistent with an increasingly active migratory swimming mode. The third is behavioral. Smolts develop a strong downstream migratory drive and begin to show rheotaxis, the tendency to orient to and move with the current rather than against it. You examine the steelhead in Raceway 8 this morning, standing at the tail end and watching the fish behavior. Approximately 60 to 70% of the fish in this raceway show advanced silvering. The parr marks are faint or absent, and the flanks have the mirror-like reflectivity of a smolting fish. Approximately 20 to 30% still show visible parr marks and a less silvery appearance, representing fish that are lagging in the smoltification process. This range of smoltification progress within a single cohort is normal. Smoltification is not synchronous across an entire population, but occurs across a window of several weeks, triggered by the same photoperiod cues, but with individual variation in the timing and completeness of the response. The smoltification window in Pacific Northwest steelhead hatcheries is closely linked to the natural increase in day length that occurs in late winter and early spring. Your raceways are uncovered, exposed to natural photoperiod, and the steelhead in them are responding to the same lengthening days that wild steelhead are responding to in the rivers beyond the hatchery fence. The hatchery's target release date for the steelhead smolts is mid-April to early May, timed to coincide with the peak of smoltification and the optimal conditions for downstream migration. A smolt released too early, before smoltification is complete, will have poor saltwater adaptation. A smolt released too late, after the smoltification window has closed and the fish has begun to desmolt, is also disadvantaged. The timing of the stocking truck is calibrated to the biology of the fish. You record your smoltification observations in the steelhead production log, estimating the percentage of each raceway population showing advanced, partial, and minimal smoltification signs. You also measure the fork length and weight of a sample of fish from Raceway 8. You dip net a sample of 30 fish, anesthetize them briefly in a dilute solution of trichine methane sulfonate M, S222, which is the standard fish anesthetic used in hatchery sampling. Measure each fish to the nearest millimeter fork length and weigh them collectively to determine average weight. Average fork length is 216 millimeters. Average weight is 112 grams. These are good pre-smolt metrics for this time of year and this species. Disease management in a fish hatchery is continuous, systematic, and preventive in emphasis. The fish in your care live at densities far exceeding what any wild population would experience, which means that pathogens, if present, have abundant hosts in close proximity and can spread rapidly. The management philosophy at a well-run hatchery is not reactive treatment of disease outbreaks, but proactive monitoring and prevention that minimizes the conditions under which disease can establish and spread. Bacterial diseases are the most common health concern in salmonid hatcheries. The major bacterial pathogens of hatchery salmonids include Flavobacterium columnar, which causes columnaris disease, affecting the gill's skin, and Fins Aeromonas salmonicida, which causes furunculosis, a systemic bacterial septicemia, Yersinia ruckeri, which causes enteric red mouth disease, or ERM, a systemic disease named for the hemorrhaging that occurs around the mouth and at the base of the fins, and Rhinibacterium salmoninarum, which causes bacterial kidney disease, or BKD, a chronic, progressive systemic infection that is particularly challenging to manage because it can be transmitted vertically from infected broodstock to offspring through the eggs. Your hatchery has a health monitoring protocol that includes daily behavioral observation of all fish during the morning mortality check and feeding, which is the frontline detection system for any health problem, monthly gill examination of sampled fish from each raceway under a microscope checking for the presence of gill pathogens, including Flavobacterium and the monogenean ectoparasites that can cause significant gill damage at high levels. Quarterly bacteriological culture of kidney tissue from a sample of fish from each population, which detects systemic bacterial infections, including furunculosis and BKD, that may not yet be producing external signs, and annual testing of the broodstock population for R. salmoninarum by the State Fish Health Laboratory using enzyme-linked immunosorbent assay, ELISA, testing, which is more sensitive than bacteriological culture for this slow-growing pathogen. This morning, as part of your routine, you examine the gills of 5 fish from Raceway 3, the raceway that had the 3 mortalities with fin erosion this morning. You anesthetize 5 fish with MS-222. Remove a small section of gill arch from the right side of each fish and prepare wet mount slides on the microscope stage in the hatchery laboratory. Under the microscope, at 40 times magnification, you examine each gill preparation for the presence of Flavobacterium columnar, which appears on a wet mount as long, slender rods approximately 5 to 8 micrometers in length, arranged in the haystack clusters, or gliding motility patterns characteristic of this species. You also examine for the presence of Ichthyophthirius multifiliis, the ciliate parasite commonly called ick or white spot, which appears as large horseshoe nucleus ciliated cells in the gill tissue, for trichidinid ciliate parasites, which appear as disc-shaped organisms with a ring of marginal denticles, and for the eggs or adults of monogenean flatworm parasites. In 3 of the 5 fish from Raceway 3, you observe occasional Flavobacterium columnar cells in the gill preparation, present at a low density. This is consistent with the fin erosion mortalities you observed this morning and suggests a low-level columnaris infection in this population. Low-level columnaris is common in hatchery salmonids at cool water temperatures and does not necessarily require treatment, but it warrants monitoring. You increase the monitoring frequency for Raceway 3 to daily for the next week and note the finding in the health log if the mortality rate increases or if the microscopic examination reveals increasing pathogen density in subsequent samples. You will consult the state fish health specialist to discuss treatment options. Treatment options for columnaris disease in hatchery salmonids are limited by the regulatory framework governing drug use in food fish. Hatchery fish are not food fish in the conventional sense, but the regulatory framework under which fish drugs are approved in the United States applies to all fish, including hatchery-produced fish that may ultimately be harvested by anglers. The only FDA-approved drugs available for use in hatchery fish are trichine methane MS-222 for anesthesia, formalin for the treatment of external parasites and saprognosis, and hydrogen peroxide for external parasite treatment. Aquaculture-approved antibiotics, including oxytetracycline and fluorophenical, can be used under a veterinary prescription, but their use requires a veterinarian-client-patient relationship and is subject to mandatory withdrawal periods before the fish can be released or harvested. Your hatchery has an ongoing relationship with a licensed aquatic animal veterinarian who provides health consultation and prescribes medications when needed. You call her this afternoon to discuss the Raceway 3 finding. After the laboratory work, you conduct the weekly inspection of the water supply infrastructure. The water supply is the single most critical component of hatchery operations. A failure in the water supply that is not detected and corrected quickly will kill fish. A partial supply failure that reduces flow to one or several raceways can deplete oxygen and accumulate ammonia to lethal levels within hours at the fish densities you carry. You inspect the supply infrastructure every week, more frequently during periods of drought, high turbidity events, or any time you have reason to believe the system may be stressed. The water supply system begins at the intake structure on the creek, approximately a quarter-mile uphill from the hatchery. The intake is a concrete diversion dam that creates a small impoundment from which water is drawn into a screened intake box and flows by gravity through a buried pipeline to the hatchery's head box, which is the distribution manifold from which individual supply pipes branch to each raceway tank and building. The entire supply is gravity-fed. There are no pumps in the primary supply system, which means there is no pump to fail and no power dependency in the primary water supply. This is a deliberate design feature of hatcheries built in the early and mid-20th century, and it remains a significant operational advantage. If the power goes out, the water keeps flowing. You walk to the intake structure first. The intake screen, which excludes debris and prevents the entry of wild fish and large invertebrates into the supply system, must be inspected and cleaned regularly. After rain events or during periods of high flow, the screen can accumulate organic debris and sediment rapidly. A partially blocked intake screen reduces flow to the hatchery and, in severe cases, can reduce it to the point where fish in the raceways begin to experience oxygen depletion. This morning, following 2 days of rain, you expect to find some screen accumulation. The intake screen has a moderate accumulation of leaf material and small sticks on its upstream face, consistent with the recent rain. You clean the screen using a stiff brush and the flow of the water itself, which carries the removed debris downstream. You also inspect the intake dam. The concrete overflow weir is intact, the impoundment level is normal, and there is no evidence of seepage at the dam abutments. The creek is running slightly above base flow from the recent rain, but is clear, not turbid. Turbid water, carrying high sediment loads, is one of the more challenging conditions for hatchery water supply management because fine sediment particles that pass through the intake screen can settle in the supply pipeline and gradually reduce flow capacity, and more critically, can pass all the way to the fish tanks, where the turbidity itself can cause gill irritation and sediment-related mortality at high concentrations. You walk back to the hatchery and inspect the head box. The head box is a concrete distribution, manifold approximately 6 feet by 8 feet, open at the top, from which the individual supply pipes for each raceway depart. The flow of cold, clear water into the head box, and the distribution of that flow to the facilities, various water consumers, is a reassuring sight at any time of day, because the flow of water means the fish are receiving oxygen and the waste products are being carried away. A head box running dry would be an emergency. This head box is not running dry. You measure the inflow rate at the head box outlet pipe using a flow meter, 1,400 gallons per minute, consistent with recent flows and adequate for current fish loads. You inspect the distribution pipes to each raceway, walking along the raceway supply lines and checking the valve positions, the pipe condition, and the flow rate at each raceway's supply end. You had already noted the partially closed valve to raceway for this morning. You verify that it is now fully open and the flow has normalized. You also check the overflow pipes, which are the emergency drain pipes at the head end of each raceway that prevent flooding if the raceway drain becomes blocked. The overflow pipes should be installed at a height above the normal water surface level, and their outlets should be inspected to confirm they are clear and functional. One overflow pipe on Raceway 9 has a small accumulation of algae at its outlet that is partially restricting the opening. You clear it with a wire brush. An overflow pipe blocked by algae growth that goes undetected will result in flooding of the raceway and potential fish loss if the drain ever becomes blocked. While today's work does not include a spawning event, the hatchery's production year revolves around the spawning season, and an understanding of spawning operations is fundamental to understanding what the fish in your raceways are and why they are here. We will describe the spawning operations in the context of this past autumn's work, which produced the eggs currently incubating in the building. Salmonid hatcheries maintain broodstock, which are sexually mature fish maintained at the hatchery, specifically for the purpose of contributing eggs and milt, the male reproductive fluid, to the hatchery's production program. Your hatchery's broodstock consists of separate populations of rainbow trout, brown trout, coho salmon, and steelhead, each managed as a distinct genetic strain. The broodstock are held in dedicated broodstock raceways, separate from the production fish, at a controlled density and feeding regimen designed to support their growth and reproductive development. Spawning readiness in salmonids is indicated by a combination of external signs and behavioral cues. Female fish approaching spawning develop a characteristic swollen abdomen as the eggs, called ova, ripen in the ovarian follicles. The vent becomes soft and slightly protuberant. In salmon species, the body color changes dramatically. Male salmon develop the characteristic hooked jaw, called a kype, and the deep red-orange coloration of spawning. Female salmon develop less extreme color changes, but become visibly darker, and their body shape changes as the abdomen fills with ripe eggs. Rainbow trout and steelhead develop the characteristic lateral pink to red band of the species, more vivid in males. Brown trout develop a rich amber-orange coloration in males. You assess spawning readiness by gently pressing on the abdomen of candidate females. If ripe, eggs extrude from the vent with minimal pressure. This is called the strip test, and it is performed without anesthesia for a quick check, or with anesthesia for a more thorough assessment. A female whose eggs do not extrude with gentle pressure is not yet fully ripe and should be returned to the broodstock raceway for additional development time. A female who extrudes eggs freely is ripe and should be spawned within the next several days, because overripe eggs that are not fertilized quickly experience quality degradation that reduces fertilization and survival rates. The spawning operation is conducted in the spawning building, which is a covered structure with concrete work surfaces, a water supply for rinsing, a drain system, and the equipment needed for egg collection, fertilization, and processing. Spawning of hatchery fish is almost always done by artificial fertilization, which means eggs are stripped from the female directly into a dry collection bowl and immediately combined with milt stripped from one or more males. The dry method of artificial fertilization, in which eggs are collected into a completely dry bowl and mixed with milt before any water is added, achieves consistently high fertilization rates because water contact initiates the fertilization activation sequence in the eggs, and any water contamination of the eggs or milt before they are mixed will reduce fertilization success. The coho spawning in November involved 22 female broodstock fish and 38 male broodstock fish. The sex ratio is skewed toward males because milt is available in essentially unlimited quantity from each male, while each female produces a fixed number of eggs, and having more males available ensures that each egg receives abundant sperm exposure during fertilization. You and your seasonal staff stripped each female individually into a pre-weighed dry stainless steel bowl, recording the female's identity by means of an internal anchor tag that was implanted in the fish at the juvenile stage. The individual egg weight estimated by the bowl weight, and the estimated egg count. Milt from 3 males was added to each female's eggs. The eggs and milt were gently combined by hand in the dry bowl, and a small amount of water was then added to activate the fertilization process. After a 3-minute fertilization period, the fertilized eggs were gently rinsed in clean water and water hardened in a large clean container. Water hardening is the process by which fertilized eggs absorb water through the egg membrane, increasing slightly in size and developing a firm, turgid texture. The water-hardened egg is much more resistant to mechanical damage than a freshly fertilized egg, which is soft and easily damaged by the pressure of other eggs. Water hardening takes approximately 30 to 60 minutes in clean, cold water. The water-hardened eggs are then counted using a volumetric counting device, which measures a known volume of eggs and uses the average egg size determined by counting a subsample to estimate the total count. The total coho egg count after water hardening was 182,000 eggs, consistent with the expected fecundity of this broodstock group based on historical records. The fertilized, water-hardened eggs were then treated with a dilute iodophore solution to disinfect the egg surface, a standard practice that reduces the surface bacterial and fungal load without damaging the developing embryo inside. After iodophore treatment and thorough rinsing, the eggs were loaded into the heath stacks at the density of 2 eggs per square centimeter. The water flow was established, and the incubation period began. The entire spawning and egg setup process for the coho cohort took approximately 8 hours across 2 days. The first day for spawning and water hardening, and the second day for counting, treating, and stacking. After lunch, which at a hatchery tends to be eaten standing up near whatever task is most pressing, you conduct the monthly population sampling for the rainbow trout in raceways 1 through 6. Monthly population sampling involves obtaining current estimates of fish number, average weight, and average length for each production group, which are used to calculate feed rations, assess growth rates against production targets, evaluate feed conversion efficiency, and project the timing of stocking events. Estimating the number of fish in a raceway is not as simple as counting them. Counting individual fish in a raceway of 30 to 60,000 individuals is not feasible in any practical sense. The fish move too quickly, are too numerous, and are too similar in appearance to allow accurate individual counting. Instead, hatcheries use volumetric counting methods that estimate total population size from a counted subsample. The most commonly used volumetric counting method in salmonid hatcheries is the volumetric or gravimetric sample method. You dipnet a random sample of fish from the raceway, weigh the sample, and count the individual fish in the sample. From the count and weight of the sample, you calculate the average weight per fish. You then weigh the entire raceway population in net loads, divide the total population weight by the average fish weight, and arrive at an estimate of total fish number. The accuracy of this method depends on the representativeness of the sample. You should sample from multiple locations in the raceway and at multiple depths to avoid biasing the sample toward fish with particular behavioral characteristics, such as the most aggressive feeders who congregate near the surface, which might not be representative of the population as a whole. You set up the weighing station at Raceway 2, which holds a group of approximately 4-inch rainbow trout. You dipnet a sample of approximately 200 fish into a 10-gallon bucket containing a small amount of water with S-222 at the anesthesia dose, which briefly immobilizes the fish for weighing and counting without causing distress. You weigh the bucket with the fish, subtract the tare weight of the bucket and water, and determine that the sample weighs 1,040 grams. You count the fish, 212. Average weight, 1,040 divided by 212 equals 4.9 grams per fish. You then dipnet the raceway in successive loads using the large hatchery net, transferring each net load to a large weighing tub on the scale, recording the weight, and returning the fish to the raceway. The total weight across 15 net loads is approximately 1,960 kilograms. You divide 1,960 kilograms by 0.0049 kilograms per fish to get an estimated population of approximately 400,000 fish. Your records show you stocked this raceway with 412,000 fry in September. You have experienced about 3% mortality since stocking, which at this stage of development is a normal and expected attrition. The population estimate of approximately 400,000 fish is consistent with expectations. You record the sampling data in the production database. Raceway 2, rainbow trout, current date, average fork length from the sample, average weight 4.9 grams, estimated population 400,000 fish, estimated total biomass 1,960 kilograms. You recalculate the daily feed ration for Raceway 2 based on the updated biomass estimate and the current feeding rate from the feed table. 1,960 kilograms times 1.4% equals 27.4 kilograms per day. The previous ration was based on the last sampling's biomass of 1,700 kilograms and was 23.8 kilograms per day. You increase the automatic feeder calibration to the updated ration, noting that the fish have grown and their feed requirement has increased accordingly. Growth rate is assessed by comparing the current average weight against the projected weight from the production target schedule. The production target schedule is a calendar of expected average weights by date for each species and cohort, derived from the weight-at-age relationship for that strain and species at your water temperature, calibrated from historical production data at this specific hatchery. Your rainbow trout in Raceway 2 are slightly ahead of the target weight for this date, which indicates good feeding conditions and feed conversion efficiency. You note this as a positive finding and continue with the other raceways. In the early afternoon, you walk the perimeter of the outdoor raceway area and check the predator exclusion equipment. Fish hatcheries are extremely attractive to piscivorous or fish-eating wildlife. The combination of large numbers of fish in confined, shallow, accessible water constitutes a food resource that animals with sufficient sensory capability will locate and exploit given the opportunity. The principal predators at your hatchery are great blue herons, belted kingfishers, common mergansers, river otters, mink, and occasionally bald eagles. All of these species are protected under federal law, which means lethal control is not an option. Exclusion, deterrence, and structural barriers are the available tools. The raceways are covered with bird netting, a fine mesh polypropylene net suspended on a framework of aluminum conduit above the raceways. The netting prevents herons and other wading birds from entering the raceway area from above, and prevents kingfishers from diving into the water. You inspect the netting for tears, gaps at the frame connections, and areas where the netting has sagged close to the water surface, which would allow a heron to stand on the net and reach through it to take fish. You find 2 locations where the netting frame connections have loosened, and the netting has dropped approximately 8 inches below its normal tension height, creating a low area that a large heron could potentially stand on. You tighten the frame connections and retension the net at both locations. The net is otherwise intact. The otter and mink exclusion is provided by hardware cloth, a welded wire mesh with 1/2 inch openings, installed as a continuous barrier around the base of the raceway walls and along the drainage channels. Otters and mink are excellent swimmers and can enter raceways through drainage channels if those channels are not protected. You inspect the hardware cloth barrier at the drainage channel entry points, checking for any areas where the mesh has been bent aside or where corrosion has weakened the wire. One section of hardware cloth at the main drainage outfall shows significant rust at 2 horizontal wires, reducing their structural integrity. You replace the damaged section with a fresh piece of galvanized hardware cloth, cutting it to size and securing it with wire staples to the wooden frame around the outfall opening. Predation losses at a well-protected hatchery are minimal. Your annual records show predator-attributed mortality of less than 0.1% of total production, which is a negligible fraction. But this low loss rate is the product of continuous maintenance of the exclusion barriers. A single mink that gains access to a raceway of small fry can kill hundreds of fish in a single night, not because it consumes them all, but because it kills far more than it can eat, a phenomenon documented in predation studies that reflects the mink's hunting instinct continuing in the presence of easily killed prey. A single otter in a raceway of fingerlings can cause thousands of dollars of production loss in hours. The exclusion barriers are cost-effective investments in proportion to what they prevent. You also check the facility's perimeter fence, which excludes unauthorized human access as well as large mammals. The fence is a 6-foot chain link perimeter, supplemented with an overhang on the outside of the top rail that angles outward and downward, making it difficult to climb from the outside. Unauthorized access to a hatchery represents risks ranging from vandalism and fish theft to, more seriously, the intentional or unintentional introduction of disease organisms or contaminants into the water supply. Your hatchery's water supply is exclusively the spring-fed creek, which originates on land managed by the state and is not accessible to agricultural or industrial contamination upstream. But the on-site water features are accessible if the perimeter is breached. The fence is intact on all sides. You note this and continue. No stocking truck is scheduled today, but stocking operations are sufficiently central to the hatchery's mission that they deserve a thorough discussion. A stocking event is the culmination of the hatchery production cycle. The fish that have been hatched, reared, fed, monitored, and maintained for months or years are loaded into a transport truck and released into the lake's streams and reservoirs, where they will spend the remainder of their lives to be caught by anglers, or in the case of the anadromous steelhead and coho, to migrate to the ocean and return as adults. The transport truck is a specialized vehicle, a tanker truck with multiple insulated fish-holding tanks in its rear compartment, each equipped with oxygen injection and aeration systems to maintain adequate dissolved oxygen during transport. The tanks hold between 1,000 and 3,000 gallons of water, depending on their size, and each tank is loaded with a calculated number of fish based on the transport density guidelines that specify the maximum pounds of fish per gallon of water for a given transport duration and water temperature. At 52 degrees Fahrenheit, the maximum transport density for rainbow trout on a transport of under 2 hours is approximately 1 pound of fish per gallon of water. For longer transports, the density is reduced to allow for the accumulation of metabolic waste products, primarily carbon dioxide and ammonia during transit. Loading the stocking truck is a physically demanding operation that requires careful coordination. Fish must be crowded from the raceways using seines, transferred via a pump and pipe system, or a gravity-fed loading chute into the truck tanks, counted as accurately as possible during the loading process, and the truck tanks monitored for dissolved oxygen throughout the loading. Fish that are crowded and handled during loading experience acute stress, reflected in the release of cortisol and catecholamines, and the transport duration should be minimized, and the fish provided with recovery time in well-oxygenated water before and during transport. Counting fish during loading is done using a counting board, a device through which fish pass single file through a narrow channel past a sensor or counter. For larger fish, individual counting is feasible and accurate. For smaller fish, such as 3-inch fry stocked into high elevation lakes, volumetric counting is used. A known volume of fish is counted to determine the fish per gallon ratio, and the total loaded volume is measured to estimate the total stocked number. The accuracy of volumetric counting for small fish is approximately plus or minus 5%, which is acceptable for management purposes. The stocking locations and stocking rates are determined by the fisheries management program, not by the hatchery. You receive stocking orders specifying the date, location, species, size, and number of fish for each stocking event. Your job is to have the correct fish ready at the correct size on the correct date. This sounds straightforward. Over a production calendar that spans multiple species with overlapping life stages and multiple stocking events distributed throughout the year, it requires precise management of growth rates, feed rations density adjustments, and timing to ensure that each cohort reaches its target stocking size within the acceptable window around its target stocking date. A group of rainbow trout that is 6 inches at stocking will be at the target size for streams where 6-inch fish are specified. The same fish at 5 inches will not meet the stocking specification. The difference between 5 inches and 6 inches is approximately 3 to 4 weeks of growth at your water temperature, and achieving that target requires accurate feed management and growth tracking beginning 6 months before the stocking date. Last week's stocking event involved the release of 80,000 catchable size rainbow trout, each averaging 11 to 12 inches in length, into 14 stream and reservoir locations across the state. The catchable size fish are the most resource-intensive product of the hatchery. They have been in production for approximately 14 to 16 months, have consumed a large quantity of feed, and require the most space in the raceways during their final months of growth. They are also, from the public fishing perspective, the product most directly connected to the hatchery's mandate. An angler who catches a 12-inch hatchery rainbow trout on opening day of the trout season is the direct beneficiary of 14 months of hatchery production. That the angler probably does not know or think about where the fish came from is consistent with the general pattern of public infrastructure. Invisible until something goes wrong, and very rarely going wrong. In the mid-afternoon, you update the broodstock management records. Genetic management is a dimension of hatchery operation that has grown substantially in importance over the past 3 decades, as the scientific understanding of hatchery fishes' genetic effects on wild populations has advanced. The fish produced at your hatchery are released into waters that also support wild populations of the same species, and the genetic interactions between hatchery fish and wild fish are a legitimate conservation concern that modern hatchery management takes seriously. The primary genetic concern with hatchery production is the potential for domestication selection, which is the unintentional selection for traits that are advantageous in the hatchery environment, but disadvantageous in the wild. Fish in a hatchery are fed on demand, protected from predators, maintained at high density, and selected for survival and growth under these artificial conditions. Over generations, natural selection in the hatchery environment favors individuals with behavioral and physiological traits suited to captivity. Reduced predator avoidance, increased boldness, higher baseline cortisol, and altered feeding behavior, among others. A fish bred and raised in a hatchery for multiple generations will, on average, be less well adapted to life in the wild than a wild fish of the same species. And if hatchery fish interbreed with wild fish, these traits can enter the wild gene pool. The management response to domestication selection is to minimize the number of generations that fish are maintained in captivity to use wild origin broodstock as frequently as possible, and to maintain genetic diversity in the broodstock population by using the largest possible number of individual broodstock fish and avoiding the disproportionate representation of any single family in the production cohort. The practice of minimizing reproductive contribution from any individual, called equalization of family contribution, requires careful record keeping of which males and females contributed to each cohort, and how many offspring were derived from each cross. Your hatchery's coho salmon program uses a wild origin broodstock supplementation strategy for the coho strain. Adults returning from the wild are captured at a weir downstream from the hatchery during the fall spawning migration. A random sample is retained as broodstock, while the remainder are allowed to pass the weir and complete their natural spawning, and the retained fish contribute their eggs and milt to the hatchery production in combination with the existing hatchery broodstock. This approach maintains a connection between the hatchery population and the wild population, bringing in new genetic material each generation. and preventing the progressive divergence of the hatchery strain from the natural population. The broodstock records you maintain include the identity of each broodstock fish assigned by internal anchor tag, the fish's origin, whether wild or hatchery reared, the date and results of any health testing, the date of spawning the cross pairings, which males were combined with which females, and the egg count and survival data from each cross. These records are used to calculate the effective population size of the broodstock population, a measure of genetic diversity that accounts for the variation in family sizes, and to ensure that the next generations broodstock are selected to maintain maximum diversity while avoiding inbreeding between closely related individuals. You also maintain otolith marking records. Otoliths are the calcite ear bones of fish, which grow continuously throughout the fish's life in a daily incremental pattern that records growth history. Hatchery fish can be marked by manipulating the otolith's growth pattern during early development, creating a chemical mark or thermal mark that is unique to the hatchery cohort and distinguishable from wild fish's otolith patterns when examined under magnification. This marking allows researchers and managers to distinguish hatchery origin fish from wild fish in the population, which is essential for evaluating the hatchery's contribution to the fishery and for assessing the straying rates, the proportion of hatchery fish that return to spawn in waters other than their release location. Your hatchery marks all coho and steelhead smolts with a coded wire tag, a small length of coated stainless steel wire injected into the snout cartilage, in addition to the otolith thermal mark, providing two independent marking systems for post-release identification. Your maintenance specialist is working this afternoon on the annual inspection and cleaning of the oxygen injection system, and you assist him for the latter part of the afternoon. The oxygen injection system is a relatively recent addition to the hatchery, installed in 2018 as part of a facility upgrade funded by a federal fish and wildlife grant. Prior to the installation, the hatchery's oxygen management relied entirely on the natural oxygen content of the incoming water, supplemented by splashboard aeration, where the water falls from supply pipes into raceways. The oxygen injection system allows the delivery of pure oxygen directly into the raceway supply water, which increases the carrying capacity of each raceway by allowing higher fish densities without oxygen depletion. The oxygen injection system uses a liquid oxygen storage tank, a cylindrical cryogenic vessel that stores oxygen at extremely low temperature, approximately -297 degrees Fahrenheit, in liquid form. Liquid oxygen is vaporized and delivered through a pressure regulator to a distribution manifold, and then through individual injection lines to each raceway. The oxygen is injected into the raceway supply water through a submerged diffuser, a device with fine pores that break the oxygen into small bubbles, maximizing the contact area between the gas and the water and improving dissolution efficiency. The annual inspection of the oxygen injection system covers the condition of the diffuser elements, which can become fouled with biofilm and mineral deposits that reduce their porosity and effectiveness, the condition of the injection lines and their connection, fittings, the calibration of the dissolved oxygen monitoring probes that control the injection rate, and the inspection of the pressure regulator and safety relief valves on the liquid oxygen storage tank. The tank itself is inspected by the oxygen supplier's service technician on a separate annual visit. You and your maintenance specialist work through the diffuser cleaning systematically, removing each diffuser element from its raceway mounting, soaking it in a dilute citric acid solution to dissolve mineral scale, rinsing it thoroughly, and reinstalling it. The citric acid soak takes approximately 20 minutes per diffuser, and with 12 raceways and 24 diffuser elements in the system, the full cleaning takes most of the afternoon. The clean diffusers produce finer, more uniform bubble patterns when reinstalled, which your maintenance specialist demonstrates by injecting a brief pulse of oxygen through the newly cleaned element and comparing the bubble pattern to a fouled element he has kept for comparison. The difference is significant. The clean element produces a dense cloud of tiny bubbles that rise slowly through the water column, maximizing contact time. The fouled element produces fewer, larger bubbles that rise quickly and dissolve less efficiently. Clean diffusers use less oxygen to achieve the same dissolved oxygen concentration in the water, which reduces the oxygen cost per pound of fish produced. Beyond the oxygen system, the physical infrastructure of the hatchery requires continuous attention. Concrete raceways develop cracks and surface deterioration from the constant wetting and drying cycles, and from the mechanical stress of fish and equipment. The water supply pipes, most of which are the original aluminum or galvanized steel lines installed in the 1940s and 1950s, and supplemented with PVC replacements over subsequent decades, require inspection and repair when corrosion or joint failures develop. The hatching building's concrete floor drains must be kept clear to prevent flooding during high-flow events. The electrical system powering the automatic feeders, monitoring instruments, and lights requires regular inspection for the damp conditions that accelerate corrosion in a hatchery environment. The age of the facility means that maintenance is a constant negotiation between the staff's capacity and the facility's needs. Deferred maintenance accumulates in old hatcheries in ways that eventually become expensive failures, and your annual budget includes a maintenance reserve that you and your maintenance specialist plan against an inspection schedule developed at the beginning of each year. The oxygen system cleaning is on schedule. The supply pipe replacement on the east side of the facility, where a section of original 1940s aluminum line is showing corrosion failures at 3 joints, is scheduled for late April when the steelhead have been stocked and the spring production pressure has eased. At 4:30 in the afternoon, you conduct the second water quality check of the day and the final rounds. The afternoon rounds are less intensive than the morning rounds, but are essential. They confirm that the water quality parameters have remained stable through the day, that no new mortalities have appeared in significant numbers since the morning check, and that the automatic feeders have functioned correctly and dispensed the programmed ration. You test dissolved oxygen at the tail end of Raceway 4, the raceway that showed the slightly elevated ammonia, and reduced dissolved oxygen this morning, following the discovery of the partially closed valve. Current dissolved oxygen at the tail end of Raceway 4 is 8.3 milligrams per liter, well within the acceptable range. The flow rate correction made this morning has resolved the issue. You test total ammonia at the tail end of Raceway 4, 0.5 milligrams per liter, down from this morning's 0.8. At the water pH of 7.4, unionized ammonia is approximately 0.02 milligrams per liter, right at the chronic toxicity threshold. This is better than this morning, but still warrants monitoring. You note the improvement and flag Raceway 4 for the morning check. You check the automatic feeders on raceways 7 through 12. The feeders are belt-driven units with a hopper that holds several days' supply of pellets. You verify the belt speed, which determines the dispensing rate, against the programmed setting for each raceway. All feeders are running at their programmed settings. You check the hopper levels. 3 feeders are at approximately 30% capacity and will need refilling tomorrow morning before the first feeding cycle. You note this in tomorrow's task list. You walk the raceways for the afternoon behavioral observation. Behavioral observation in the afternoon is less focused on mortality detection, which you will do again first thing tomorrow morning, and more focused on feeding response and population health indicators. A raceway of fish that responded actively to the morning feeding should show a calm, regular distribution pattern by mid-afternoon. Fish holding their position in the current, making occasional feeding, strikes at real or imagined particles in the water column, but not showing the frantic surface activity of hungry fish or the lethargic bottom resting of sick fish. You observe each raceway for approximately 30 to 60 seconds, walking the full length at a deliberate pace. Raceway 3, which had the fin erosion mortalities this morning, shows a normal distribution pattern with no obvious behavioral anomalies. This is reassuring. You conduct the final check of the incubation building, examining the hatching coho stacks and the brown trout fry tanks. The coho alevins in the stacks look healthy. They are lying quietly on the tray surface and in the small amount of water covering it, showing the normal, infrequent tail wag movements of alevins at this stage of development. You scan the trays for white dead eggs and remove 2 from one tray that were not present this morning. The absence of additional saprolegnia growth on stack 14, where you treated a small colony this morning, is a positive sign. You make the evening eau-de-four rinse of the stack 14 tray as a precautionary follow-up treatment and note it in the egg incubation log. The brown trout fry in the indoor tanks show active feeding behavior during the afternoon feeding you conduct at 4:45. You drop a measured ration of crumble into each tank, and the fish respond immediately and aggressively, confirming good appetite and health status. You note the feeding response as active for all brown trout tanks. You check the demand feeders in the smaller fry tanks, refilling 2 that have run low, and confirm that the fish are triggering them by observing the pendulum mechanism moving as fish bump it from below. Everything is functioning. You note the satisfactory state of the afternoon checks in the daily log. You fill out the daily production log before leaving the hatchery. The daily log records morning and afternoon water temperatures and dissolved oxygen at key monitoring points, any mortalities found, and their probable cause, any treatments administered, any equipment anomalies, the feed rations applied to each raceway, and building the water quality test results, and any observations about fish behavior or condition worth noting for continuity with the next day's shift. Your junior colleague will conduct tomorrow morning's first check. The log gives them the current state of each population and the flagged items requiring their attention. You have completed a day at the Fish Hatchery. During this day, you conducted 2 complete rounds of the facility, covering 12 outdoor raceways, 6 indoor fry and fingerling tanks, 24 coho egg incubation stacks, and all associated infrastructure. You found and removed 18 mortalities, examining each for cause of death, and noting 2 cases of probable columnaris bacterial infection warranting monitoring. You conducted water quality testing at morning and afternoon, identifying and correcting a flow rate deficiency in Raceway 4, and monitoring the associated ammonia improvement. You fed 4 million fish across 4 species in 4 life stages, calculating rations from the feed table, adjusting automatic feeder settings, and hand broadcasting feed to the smaller fish. You examined alevin development in the hatching coho stacks and treated a small saprolegnia colony. You collected gill samples from 5 fish in Raceway 3 and examined them microscopically, finding low-level Flavobacterium columnare in 3 fish. You inspected and maintained the intake structure the head box, and the distribution system. You conducted the monthly population sampling for Raceway 2, recalculating the feed ration based on the updated biomass. You inspected and repaired predator exclusion netting and perimeter barriers. You assisted with the annual oxygen diffuser cleaning and reinstallation. You updated the broodstock genetics records and smoltification observation logs. You completed the daily production log and left a briefing note for tomorrow's first check. The 4 million fish in this facility are producing, at this moment, a continuous demand for oxygen, food, and clean water that does not pause when you leave for the evening. The water continues to flow through the raceways. The automatic feeders continue their programmed cycles. The hatching coho alevins continue absorbing their yolk sacs according to a schedule driven by accumulated thermal units and not by the hatchery's staffing calendar. Tomorrow morning at 6:30, the first thing you or your colleague will do is walk those raceways and look at the fish. State fish hatcheries are not universally admired within the fisheries science community. The question of whether hatchery supplementation programs are net beneficial or net harmful to wild salmonid populations is a genuine scientific debate with substantial evidence on multiple sides, and the answer is almost certainly it depends. It depends on the species, the population, the management goals, the genetic practices, the stocking location, and the condition of the wild habitat. A hatchery that produces steelhead for a river system, whose wild run has been reduced to a few hundred fish by decades of habitat degradation, is serving a different function than a hatchery that produces rainbow trout for recreational angling in a reservoir with no wild trout population. The debate about hatcheries is a debate about specific programs in specific contexts, and the answer to whether any given hatchery program is beneficial requires knowing the specific goals, the specific fish, and the specific place. What is not in debate is that the fish in your raceways are alive because someone does this work every day. They were alive yesterday because someone did this work yesterday. They will be alive tomorrow because someone will do this work tomorrow. The work is routine. The fish do not know it is routine. The fish do not know anything in particular. They are fish. They face into the current they eat when food appears, and they are alive in the cold clear, spring-fed water of a hatchery built 87 years ago by men with horse-drawn equipment, who did not think about the fish science debates of the 21st century, but who built the intake dam and the distribution pipes straight and true, and built them to last, and here you are, filling the demand feeder. Tomorrow morning's first check is at 6:30. Raceway 4's ammonia should be retested first. The coho alevin development is approximately 10 to 12 days from first feeding presentation. The steelhead smolts are approximately 6 weeks from their stocking window. These things will still be true tomorrow. Good night.